Welcome back to another episode of Stoked About Science. This is our second one about standing waves. Basically, how the heck are these standing waves formed? Now remember, a standing wave doesn't appear to be moving left or right, which is why it's called a standing wave. Here Carson is wiggling in slow motion a chain. It's actually the downspout of a rain gutter. And you can see that when it hits the end, it seems to be reflected back upside down. That's like a key point to look at. I'm going to show you here in slow motion me doing the same thing with a slinky. Here's the pulse, goes down, hits the end, comes back upside down. Every time it hits the end, the boundary, it flips itself over. So I've got a simulation here that is a little bit older, but it does a great job of illustrating how standing waves form. As soon as that wave hits the wall, it's reflected back upside down, and the wave that's going and the wave that's coming back start interfering with each other. And where they match up perfectly, you get a really big loopy spot, or an antinode, and when they cancel each other out, you get nothing, which is a node, a spot that doesn't move at all. So as I kind of step through these, you can see that when they match up, the loopy part's really high, the wave is, and when they cancel out, then you get just the solid black line in the middle. You can see they've got A and N's on the line there to show you where the nodes and the antinodes are. So places where the waves are matching up, we're getting constructive interference, and places where they're canceling out because they're opposite, we're getting destructive interference. So here I'm back to the slinky, and if I shake it at a certain frequency, I'll get the first possible standing wave. It's really pretty boring. But if I shake it twice as fast as the original, then I get the second possible standing wave, which is really pretty interesting. It's canceling in the middle and giving me a node, and they're adding together on those two sides there and giving me antinodes. Now I'm going to shake it 3 times as fast, and you can actually see that there's 3 antinodes there. Well, we're back to the chain again, and as Carson shakes it with just the right frequency, he'll set up that second possible standing wave, the interesting one. You know, the one that's surprising because it cancels in the middle and you just don't think it, you just wouldn't expect it to, really. So you got a node in the middle and then the 2 antinodes. This was actually the idea of my younger son, who's 8, who grabbed the chain and said, "Look, Dad, we can make those waves like you were on the slinky." I was pretty impressed. I'd never thought of that. Now remember, this is all happening because the wave that's going and the wave that's reflected have just the right timing, so they could create areas of destructive and constructive interference. So here with the original elastic string that we started the first video with, you're getting now the 3rd standing wave, 3 loops, and then I turn the frequency up so it's 4 times the original, and we're getting the 4 loops, 4th possible standing wave. Turn it up again, we're getting 5. That's the 5th possible standing wave. We get 6. And then the last one I can do that shows up on video at least is the 7th standing wave. So the next video I will show you in this series will be how to make one of these yourself pretty cheap at home and wow all your friends. Hey, thanks for watching.